2 trillion galaxies. That's what lives inside our observable universe, a sphere 46.5 billion light-years across. It sounds like everything. It sounds like more than anyone could ever need. And it is, genuinely, staggering. But here's what nobody mentions right after they say that number. It's almost certainly a tiny fraction of what actually exists. Not because our telescopes are too small, because the physics that made our universe livable also guaranteed that most of it would be hidden from us, on purpose, structurally, baked in. And tonight, we're going to follow that math all the way to the edge and then past it as far as the equations let us go. Get comfortable, hit subscribe. You're going to want to be here for this. Part 1. The knife edge we shouldn't be on. There is a number so precise, so impossibly exact, that when physicists first calculated what it should be versus what it actually is, some of them genuinely wondered if the universe had been set up by something that knew what it was doing. That number is called omega, and omega describes the shape of everything. Not the shape of a galaxy, not the shape of a supercluster, not even the shape of the observable universe in the conventional sense. Omega describes the overall curvature of space itself, the geometry of the cosmos at the largest scale we can measure. And when the Planck satellite, the most precise cosmic measuring instrument humanity has ever built, came back with its final data, the value it returned for omega was 1.000 plus or minus 0.005. In other words, the universe is flat. Not roughly flat, not approximately flat, flat to within 0.5%, measured across a sphere 93 billion light-years in diameter. Now, before you move on from that sentence too quickly, let's sit with it for a moment. 93 billion light-years. A single light-year is about 5.88 trillion miles. Multiply that by 93 billion, and you have a number so large that if you tried to write it out in standard notation, the ink would run dry several times over. Across that entire expanse, across a volume of space so enormous that the human mind genuinely cannot form a sensory picture of it, we have measured the geometry of reality and found it balanced on a knife edge with a precision of 0.5%. That should bother you, not in a frightening way, but in the way that a magic trick bothers you when you cannot figure out how it was done. Because here is the thing about flatness in cosmology. It is not a stable condition. It is not a resting state that space naturally settles into over time. It is the opposite of that. Flatness, in the equations that govern the evolution of the universe, is what physicists call an unstable fixed point. Think of it like trying to balance a pencil on its tip. You can do it for a moment with extraordinary care, but the slightest nudge in either direction sends it falling, and the longer time passes, the further from vertical it gets. The universe works the same way. If omega had started out even slightly above 1, even by a tiny fraction, the self-gravity of everything in existence would have been just strong enough to win the war against expansion. Space would have reached a maximum size and then collapsed back inward, ending in what cosmologists call the Big Crunch. We are talking about a universe that might have lived for a few 100,000 years, maybe a few million, before folding back on itself into nothing. No stars, no planets, no anything with enough time to form. And if omega had started slightly below 1, the opposite catastrophe would have played out. Expansion would have won decisively. Space would have stretched apart so quickly that matter never had the chance to clump together under gravity. You would have ended up with a universe of thinning, cooling gas spreading outward forever into a featureless, dark emptiness. No galaxies, no stars, no carbon, no you sitting wherever you are right now, watching this. The window between those two outcomes, between collapse and eternal dispersal, is extraordinarily narrow. And here is where the number becomes staggering. For the universe to look as flat as Planck measured it today, for omega to be that close to 1 at this moment in cosmic history, the initial value of omega at the very first instant of the universe, at what physicists call the Planck time, 10 to the power of negative 43 seconds after the beginning would have had to be equal to 1 to within 1 part in 10 to the power of 62. Write that out. 1 followed by 62 zeros. That is the denominator of the precision required. That is how impossibly exactly, the initial conditions of the universe needed to be calibrated for everything you see around you to exist. If the initial omega had differed from 1 by even a single unit in the 62nd decimal place, the universe would have either collapsed or dispersed long before a single star ever ignited. This is what cosmologists call the flatness problem. And calling it a problem is something of an understatement. It is not the kind of problem where you shrug and say the universe just happened to start that way, because that answer, taken seriously, requires you to accept that out of all the possible starting configurations for a universe, the effectively infinite range of values that omega could have taken, the one that actually occurred was so finely tuned that it makes winning the lottery 17 times in a row look like a statistical certainty by comparison. The flatness problem is not a puzzle about measurements being slightly off. It is a puzzle about why the universe should not exist in the form it does. And here is where the story begins to open up into something much larger. Because physicists did not simply throw their hands up at this impossibility, they found a mechanism, or rather, they proposed one. A mechanism so extreme, so violent, and so brief that it left almost no direct trace in the observable universe, yet whose consequences are written into literally everything we can see. That mechanism is called cosmic inflation. And once you understand what inflation actually does, not just to the flatness problem, but to the very boundaries of what is observable, the universe starts to look very different from the one most people picture when they look up at the night sky. Inflation is not a gentle process. It is not the ordinary expansion of space that has been going on for the last 13.8 billion years. Inflation is a period in the very early universe, lasting somewhere between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the beginning, a window so brief that expressing it in human timescales is almost meaningless, during which space underwent exponential expansion on a scale that has no analogy in anything we experience. The universe grew by a factor of at least 10 to the 26th. Some models suggest far more. To get a feel for that number, if you took a single atom, something already invisible, already beyond the threshold of direct human perception, and inflated it by that factor, it would end up larger than the entire observable universe we see today. What inflation does to the flatness problem is elegant in its brutality. Imagine you are standing on the surface of a sphere. If the sphere is small, the size of a basketball, the curvature is obvious. You can feel it underfoot, you can see it at the horizon. But as the sphere gets larger, the curvature becomes less apparent. The surface starts to feel flatter and flatter from your vantage point. By the time you are standing on something the size of Earth, the ground feels completely flat, even though you are actually living on a ball. Now take that process and multiply it by 10 to the 26th. Any curvature that existed in the early universe, any deviation from flatness that omega might have started with, would have been stretched so completely, so overwhelmingly, that from our vantage point inside the post-inflation universe, it would be undetectable. Inflation does not require omega to have started exactly at 1. It takes whatever starting value omega had and drives it to 1 with such force that the original value becomes cosmologically irrelevant. Inflation solves the flatness problem. But solving a problem in physics rarely comes for free. Every solution costs something, and what inflation costs is something most people have never fully reckoned with. Because if inflation stretched space by a factor of at least 10 to the 26th, That stretching did not stop neatly at the edge of what would later become our observable universe. It stretched everything. It stretched regions of space that were, before inflation, in causal contact with our region. Regions that could theoretically have been seen or interacted with, and pushed them so far away that no signal traveling at the speed of light will ever reach us from them. Not in 1,000,000,000,000 years, not in 100,000,000,000,000,000 years, not ever. The universe we can see, the sphere 93 billion light-years across, containing roughly 2 trillion galaxies, is not the universe. It is a tiny patch of a much larger structure. And that larger structure was hidden from us, not by accident, not by a lack of telescope power, but by the very same physics that made our existence possible in the first place. The thing that solved the flatness problem is the same thing that guaranteed we would never see most of reality. There is a calculation that tries to put a lower bound on how large the actual universe must be. Researchers Vardanyan, Trotter, and Silk published their Bayesian analysis in 2011, working from the flatness constraints in the Planck data, and what they found was that under the simplest inflationary models consistent with what we observe, the real universe must be at least 251 times the radius of our observable sphere. 251 times. That translates into a volume roughly 10 million times larger than everything we have ever seen or mapped. And that is the minimum. That is the conservative number. Under many reasonable models, the actual size is incomparably larger than that possibly infinite. This is not fringe science. This is not the speculation of a theorist on the margins of the field. This is what you get when you take the Planck satellite's measurements seriously and follow the mathematics wherever it leads. The conservative reading of mainstream cosmology is that we are trapped inside a causal bubble, a sphere defined not by the extent of the universe, but by the distance light has had time to travel since the beginning and beyond. That bubble lies a structure so enormous that describing it as more universe barely captures what we mean. So here is the question that will thread through everything we are about to discuss. What kind of physics creates a universe where most of it is permanently hidden from anyone who could ever look? Not hidden by accident, not hidden until we build better instruments, but hidden by structure, hidden by the very equations that govern how space grows. That is what we are going to find out. And I will warn you now, the answer does not get more comfortable the closer you look. It gets stranger. Part 2. The sphere you are trapped inside. Let's get specific about where you are. Right now, as you watch this, you are sitting at the exact center of a sphere with a radius of approximately 46.5 billion light-years. Not near the center, not close to the center, at the precise geometric center. And so is every other observer in the universe, no matter where they are. That is not a philosophical statement about human specialness. It is a direct consequence of how observation works in an expanding universe, and understanding it properly is the first step toward grasping just how much is hidden from us by the physics of inflation. The observable universe is defined by a simple constraint. The distance light has had time to travel since the universe became transparent, roughly 380,000 years after the beginning, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen and stop scattering every photon that tried to move. Before that moment, the universe was a plasma, an opaque fog of charged particles so hot and dense that light could not travel freely through it. After that moment, photons were released and began their journey. The most ancient photons we can detect, the ones that have been traveling toward us since that very moment of transparency, have been in transit for 13.8 billion years. They are the oldest light in the universe. But here is where intuition breaks down, and it is worth pausing on this because it trips people up every time. Those photons did not travel 46.5 billion light-years in 13.8 billion years by moving faster than light. Space itself has been expanding the entire time they were traveling. The universe kept growing while the photons were in motion, stretching the distance between their origin point and us. By the time they arrive, the object that emitted them is now about 46.5 billion light-years away in what cosmologists call comoving distance, the distance accounting for expansion. This is the difference between the light travel distance and the actual current distance, and it is crucial. The edge of our observable sphere is not 13.8 billion light-years out. It is 46.5 billion light-years out, because the universe kept growing while the light was crossing it. Every observer in the universe, no matter where they are located, sees themselves at the center of their own sphere of this size. An alien civilization sitting in a galaxy near what we perceive as our observable edge has its own observable sphere centered on itself, overlapping with ours in some regions and extending far beyond ours in directions we cannot see. Their sky contains galaxies we have never seen and never will, and their observable sphere is just as complete seeming from the inside as ours is. This is the illusion of totality, the way a finite local window onto a larger structure can feel from the inside, like the whole thing. Inside our sphere, the numbers are extraordinary. Recent estimates, building on the work of Consolis and colleagues published in 2016, suggest there are approximately 2 trillion galaxies within the observable universe. 2 trillion. For context, if you tried to count them at 1 per second, without stopping, without sleeping, without pausing for any reason, it would take you over 63,000 years to reach 2 trillion. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, and the Milky Way is, cosmically speaking, a fairly ordinary galaxy, not the smallest, not the largest, just one of 2 trillion. The observable universe contains, by most estimates, somewhere in the range of 10 to the power of 24 stars. That is a 1 followed by 24 zeros. More stars than grains of sand on every beach and every desert on Earth combined, multiplied several times over. And yet, as we established, this is a tiny fraction of the total. The central thread running through everything we are exploring is the consequence of inflation, that the same mechanism which solved the flatness problem also pushed the overwhelming majority of reality beyond any horizon we can ever reach. Those 2 trillion galaxies are the local neighborhood. The full structure is something we can only infer from the physics, never observe directly. The boundary of our observable sphere has a name and a physical reality. It is called the cosmic microwave background, and it is one of the most extraordinary things in the sky, not because of what it is, but because of what it tells us about the limits of our view. The CMB is not a wall, and it is not empty space. It is the surface of last scattering the shell of the universe at the moment it first became transparent. Every direction you look in the sky, if you could tune your eyes to the right frequency, you would see this glow, a nearly perfect black-body radiation field at a temperature of 2.725 Kelvin, or about negative 270.4 degrees Celsius, barely above absolute zero. The CMB is not the edge of the universe. It is a time boundary the furthest back in time we can see using electromagnetic radiation of any kind. Beyond it, in every direction, space continues. It continued before the universe became transparent in the form of that opaque plasma, and it continues beyond the range of the CMB in the sense that after inflation, vast regions of space were pushed outside our causal contact entirely. The CMB is not where the universe ends. It is where our line of sight ends, for now, using light. There are signals that come from beyond the CMB in the sense of being older. The cosmic neutrino background, for instance, decoupled from matter about 1 second after the beginning 380,000 years before the CMB photons were released. Neutrinos barely interact with matter at all, so they streamed free much earlier. In principle, detecting that background would let us see the universe as it was in its first second. In practice, we have not yet built a detector sensitive enough to capture it directly, though its presence is inferred from the CMB data itself and from our models of early universe nucleosynthesis. And even beyond the neutrino background, there are gravitational waves from inflation itself, ripples in the fabric of space-time, generated when inflation stretched quantum fluctuations to cosmic scales. These gravitational waves, if detected, would be the most ancient signal possible, encoding information from the inflationary epoch itself. We have not directly detected them yet, though indirect evidence in the CMB's polarization pattern, specifically a component called B-mode polarization, may eventually reveal them. The night sky, then, is not a window onto the universe. It is a partial map, a local record, a two-dimensional projection of a sphere that is itself just one region of a far larger structure. The familiar feeling of looking up and seeing the whole cosmos spread out above you is an illusion produced by the limits of our observation. You are seeing your neighborhood. You are not seeing the city, let alone the continent, let alone everything that inflation stretched beyond your reach. And the reason that larger structure is hidden is precisely the reason it could support your existence at all, because inflation stretched it flat, stretched it smooth, and in doing so, stretched most of it past every boundary you could ever cross. The observable universe is not a description of what exists. It is a description of what the physics of spacetime permits us to reach. Part 3. The Four Horizons and Why They Don't Agree. One of the most persistent confusions in cosmology is the idea that there is a single edge to the universe, a line somewhere out there beyond which nothing exists, or beyond which our telescopes simply cannot see. The reality is more complicated and considerably stranger. There are actually several different horizons in cosmology, each defined by a different physical constraint, and they do not agree with each other. Understanding why they differ is essential for understanding what inflation actually did and what it means for the permanent hiddenness of most of reality. The particle horizon is what most people mean when they talk about the observable universe. It sits at approximately 46.5 billion light-years and marks the farthest distance from which light could have reached us in the history of the universe, accounting for expansion. Anything within this sphere has, at some point, been in causal contact with us. Information could have traveled between us and those distant objects at least once. This is the horizon shaped directly by the age of the universe and the rate of its expansion. Inflation determined its character by flattening and smoothing the region we inhabit, and by establishing the initial conditions from which everything inside this sphere evolved. But then there is the cosmic event horizon, which sits at a much closer distance of about 16.6 billion light-years. This is not the horizon of what we can see. It is the horizon of what we can ever interact with, the boundary beyond which, given the current and projected future rate of cosmic expansion driven by dark energy, any signal we send today will never reach its destination, and any signal sent from beyond this point will never reach us. It is a horizon defined not by the past, but by the future, by the acceleration of expansion that is actively widening the gulf between us and distant galaxies. The Hubble sphere is different again. It sits at about 14.4 billion light-years and marks the distance at which galaxies are currently receding from us at exactly the speed of light. Inside the Hubble sphere, galaxies move away from us slower than light. Outside it, they recede faster than light. This does not violate relativity, it is space itself expanding, not objects moving through space, but it does mean that photons, currently outside the Hubble sphere, but trying to reach us, are actually losing ground. They are moving toward us through space, while space itself carries them away faster than they can approach. Eventually, as the universe expands, the Hubble sphere grows, and photons that were initially losing ground find themselves in a region of slower recession and can finally start making progress. And then there is the future visibility limit, about 62 billion light-years in co-moving distance, which marks the farthest objects that will ever become visible to us as the universe ages, including photons currently in transit that have not yet arrived. Here is what ties all of these together and brings us back to the central story. Right now, we can see galaxies, some of them clearly, in beautiful detail that we will never be able to visit, never be able to communicate with, and that will eventually disappear from our sky entirely. Dark energy is accelerating the expansion of space. Over time, distant galaxies will redshift beyond detectability, their light stretching to wavelengths too long for any instrument to capture. The observable universe, in causal terms, is actually shrinking, not in the sense that the sphere of past visibility is getting smaller, but in the sense that the set of objects we can ever hope to interact with is contracting. Inflation set the initial scale of what is hidden. Dark energy is continuing to hide more of it as time passes. The boundary was built into the physics of this universe from its earliest moments, and it is being reinforced by every second of ongoing expansion. Part 4. Drawing triangles across the universe. Here is a question that sounds absurd on its face. How do you measure the geometry of the universe? Not the shape of Earth, not the curvature of space-time around a massive object, but the overall global curvature of the cosmos itself. How do you draw a triangle big enough to test whether the angles add up to 180 degrees or something different? The answer involves the cosmic microwave background, and it is one of the most elegant pieces of observational cosmology ever attempted. In a flat universe, the rules of Euclidean geometry apply at the largest scales. The angles of a triangle add up to 180 degrees. Light travels in straight lines that stay parallel. But in a positively curved universe, one with omega greater than 1, like the surface of a sphere, parallel lines eventually converge, and the angles of a large enough triangle add up to more than 180 degrees. In a negatively curved universe saddle-shaped, with omega less than 1 parallel lines diverge, and triangle angles sum to less than 180 degrees. The CMB gives us a ruler. In the very early universe, before the surface of last scattering, sound waves were traveling through the hot plasma pressure waves, driven by the competition between radiation pressure pushing outward and gravity pulling inward. These waves had a characteristic scale determined by how far sound could travel in the age of the universe at that time. When the universe became transparent and the CMB was released, those sound waves froze in place, leaving a pattern of slightly hotter and slightly cooler regions imprinted across the sky. The characteristic scale of those frozen waves, the distance between the peaks and troughs, is known extremely precisely from first principles of plasma physics. It acts as a standard ruler. Now, if you know the physical size of that ruler, and you can measure the angle it subtends across the sky, the angle it appears to span from our vantage point, you can calculate the geometry of the space through which its light has been traveling. In a flat universe, a ruler of a given physical size at a given distance will appear at a specific angular size. In a positively curved universe, it will appear larger. In a negatively curved one, it will appear smaller. This is the cosmic triangle test, and the CMB angular power spectrum, the pattern of peaks and troughs in its temperature fluctuations, carries the answer. The first major modern result came from the Boomerang experiment, a balloon-borne observatory that circumnavigated Antarctica in 1998 and 2000, measuring the CMB at degree scales with unprecedented resolution. Boomerang found that the first acoustic peak in the CMB power spectrum sat at a multipole moment of approximately 220, exactly where flat geometry models predicted it. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, which operated from 2001 to 2010 and refined those measurements dramatically. And then came Planck, the European Space Agency satellite, that operated from 2009 to 2013 and returned the most precise CMB data ever collected. Planck confirmed flatness at the level we have already discussed, omega equals 1 to within 0.5%. The acoustic peaks fell exactly where flat geometry models predicted. Independent confirmation came from baryon acoustic oscillations, the same frozen sound waves detected not in the CMB, but in the large-scale distribution of galaxies. The pattern of galaxy clustering across the universe carries an imprint of those early pressure waves, and that imprint, measured across surveys of hundreds of millions of galaxies, agrees with CMB flatness measurements to extraordinary precision. But there is a wrinkle, and it is the kind of wrinkle that keeps cosmologists awake at night. The Planck data showed a slight anomaly in the lensing of the CMB, the way the CMB's temperature pattern is blurred and shifted by the gravitational pull of intervening matter. The lensing signal was slightly stronger than flat geometry models predicted, hinting at roughly 2 to 3 sigma significance, not enough to declare a discovery, but too large to ignore at a slightly positively curved universe. If real, this would push omega just above 1 and imply a finite spherical universe rather than an infinite flat one. The tension has not been resolved. Combined datasets that include galaxy surveys and baryon acoustic oscillations still favor flatness. But the Planck lensing anomaly is a persistent reminder that our measurement, as precise as it is, still carries uncertainties, and the implications of those uncertainties, as we will see, are enormous. Because this is exactly where the connection to inflation becomes critical again. The extreme flatness that Planck measured, that precision of 0.5% across the entire observable sphere, is not something that could exist without inflation or something functionally equivalent to it. Classical Big Bang cosmology, without an inflationary phase, cannot produce a universe this flat. And inflation, as we have established, does not stop at the edge of our observable sphere. It stretched far beyond it. The same measurement that confirmed flatness is the measurement that implies everything we cannot see. Part 5. The flatness problem. Why this shouldn't exist. Let's go deeper into the mathematics of why flat is so dangerous. Because I think it is easy to hear 1 part in 10 to the 62 and let it wash over you as just another big number in a field full of big numbers. It is not. It is something categorically different from other fine-tuning results in physics, and sitting with it properly is essential for understanding why inflation is taken so seriously by so many physicists. In standard Big Bang cosmology, without inflation, omega obeys a specific evolution equation as the universe expands. The deviation of omega from 1, let's call it the quantity, omega minus 1, grows with time during the matter-dominated era, and grows even faster during the radiation-dominated era that preceded it. What this means, technically, is that omega equals 1 is an unstable fixed point in the dynamical equations. Just as the pencil balanced on its tip will always fall, a universe with omega even slightly away from 1 will evolve away from 1 over time. The deviation doesn't stay small, it grows. Run that equation backward in time. Today, omega equals 1 to within 0.5%. Go back 10 billion years to the era when the first stars were forming. Omega had to have been even closer to 1 at that point. Go back to the epoch of Big Bang nucleosynthesis, about 3 minutes after the beginning, when the first protons and neutrons were fusing into helium and deuterium. At that point, omega had to equal 1 to within roughly 1 part in 10 to the 15th. Go back to 1 second after the beginning, 1 part in 10 to the 18th. Go back to the Planck time 10 to the power of negative 43 seconds, the earliest moment at which our physics can say anything meaningful about the universe. 1 part in 10 to the 62, 1 followed by 62 zeros. That is how closely omega had to match 1 at the beginning, not as an approximation. As a precision requirement imposed on us by the equations of general relativity applied to the expanding universe. Now, is there a physical reason for this? Is there some principle that would naturally set omega to exactly 1? In standard Big Bang cosmology, there is not. There is no symmetry, no conservation law, no known physical mechanism that drives omega toward 1. It is purely an initial condition. And asking why the initial conditions were so precisely tuned is, in standard cosmology, like asking why a bullet fired from an enormous distance hit an exact target the size of a proton. There is no mechanism. You have to assume it was aimed. The flatness problem connects directly to the horizon problem, and the two together make the case for inflation almost ironclad. The horizon problem is this: the CMB temperature is uniform across the entire sky to 1 part in 100,000. Everywhere you look in opposite directions across the sky, regions that in standard Big Bang cosmology were never in causal contact, separated by distances greater than light, could have crossed in the age of the universe at the time the CMB was emitted. The temperature is the same. How? Two regions that have never interacted cannot, in general, be expected to have the same temperature. If you put a hot cup of coffee and a cold glass of water on opposite ends of a very long table and they never come into contact, they will not equilibrate. They will stay at different temperatures. Yet the CMB is telling us that the universe achieved thermal equilibrium across distances larger than any signal could have crossed. In standard Big Bang cosmology, this is simply inexplicable. Inflation solves both problems with the same mechanism. Before inflation, the region that would eventually become our entire observable universe was small enough, much smaller than an atomic nucleus, that all of it was in causal contact. Thermal equilibrium could be achieved. Curvature could be smoothed. And then inflation stretched this tiny, smooth, flat, equilibrated patch into something vastly larger than our observable sphere. The CMB is uniform because the entire observable universe was, before inflation, a single, causally connected region, and the universe is flat because inflation drove out every trace of curvature from our observable patch and buried it so far beyond our horizon that it will never come back to haunt us. There is a third problem that inflation solves, sometimes called the monopole problem. In the extreme heat of the early universe, quantum field theory predicts that phase transitions should have occurred as the universe cooled, transitions similar to water freezing into ice, but occurring in the fundamental fields of physics rather than in molecules. These transitions should have produced exotic particles called magnetic monopoles, hypothetical particles with a single magnetic pole, north or south, but not both. Grand unified theories, which attempt to unify 3 of the 4 fundamental forces, predict that monopoles should have been produced in enormous numbers in the early universe. But we have never detected a single one. Either they do not exist, which would rule out a large class of unified theories, or something diluted them to undetectable concentrations. Inflation dilutes them perfectly. If monopoles formed before inflation, the subsequent exponential expansion would have spread them across such an enormous volume that the expected density within our observable universe today would be essentially 0, consistent with what we observe. 3 unsolved problems in classical Big Bang cosmology. One mechanism inflation that solves all 3 simultaneously. This is not the usual story in physics, where you get one solution to one problem. This is a single physical process that resolves 3 independent paradoxes with one stroke. That is powerful. That is the kind of convergence that makes physicists take a theory very seriously even before it has been directly confirmed. But as we keep returning to, every solution has a cost. Inflation solving the flatness problem means inflation stretched our observable patch out of a much larger region. Inflation solving the horizon problem means that the regions now beyond our horizon were, before inflation, part of the same small patch that equilibrated with ours, and inflation pushed them past the boundary. Everything that was originally in causal contact with us, that shared our early equilibrium, that experienced the same smooth initial conditions, most of that is now permanently beyond reach. We are living in a fragment of what was once a unified whole, and the fragmentation was permanent. Part 6. Inflation, the expansion that hid reality. The story of inflation begins with a problem that has nothing to do with flatness or horizons. It begins with Alan Guth, a young particle physicist who in the winter of 1979 and 1980 was working at Stanford, trying to figure out why we had never detected magnetic monopoles. He was not thinking about cosmology in the grand philosophical sense. He was thinking about a very specific prediction of a very specific class of particle physics theories, and he was troubled by the mismatch between what those theories predicted and what experimentalists had found in accelerators and detectors. The solution Guth arrived at what he called a spectacular realization, according to his research notes from that period, was that a brief period of exponential expansion in the early universe would not only dilute monopoles to undetectable concentrations, but would simultaneously solve the flatness problem and the horizon problem. He published in 1981, and the paper landed in the field of cosmology like a stone thrown into still water, sending ripples in every direction. The mechanism Guth originally proposed has been refined significantly since then, but the core idea remains. In the very early universe, the dominant energy was not matter or radiation, but the energy of a field specifically, what physicists call a scalar field, which Guth modeled as the energy associated with a phase transition in grand unified theories. This field was stuck in what physicists call a false vacuum, a state that is locally stable but not at the lowest possible energy. Think of a ball sitting in a shallow depression on a hillside. The ball is stable for the moment, but if it were to get over the rim of the depression, it would roll down to the valley below. The ball is in a false vacuum. The valley is the true vacuum, the lowest energy state. While the inflaton field, as it is now generically called, sat in this false vacuum state, it had a peculiar property. It acted like a cosmological constant, a form of energy that permeates space uniformly and does not dilute as space expands. This is the same kind of energy we associate today with dark energy, but at an energy scale roughly 120 orders of magnitude higher. An energy so extreme that it drove exponential expansion at a rate that makes the current cosmic expansion look essentially frozen by comparison. The expansion is genuinely exponential, not linear, not polynomial, but exponential, meaning space doubles in size in some fixed, very short time interval, then doubles again in the same interval, then doubles again. If the doubling time is, say, 10 to the power of negative 37 seconds, then in 10 to the power of negative 36 seconds, space has doubled 10 times, growing by a factor of roughly 1,000. In 10 to the power of negative 35 seconds, it has doubled 100 times, growing by a factor of 10 to the 30th. The number that emerges from the models for the total growth factor is at minimum around 10 to the 26th, and in many models considerably larger, depending on the details of how long inflation lasted. To understand what this means for the relationship between inflation and the observable universe, it helps to work backward. The observable universe today has a radius of 46.5 billion light-years. Before inflation, the region that would eventually expand into our observable universe was smaller than a proton, perhaps much smaller, depending on the specific model. After inflation expanded it by that minimum factor of 10 to the 26th, it became vastly larger than the observable universe. The portion of the inflated region that falls within our observable sphere, the portion we can see, is a tiny fraction of the total volume inflation created. Andrei Linde, a Russian-American physicist who became one of the central figures in developing inflationary cosmology, introduced what became known as chaotic inflation in the early 1980s. Linda showed that inflation did not require exotic grand unified theory phase transitions. It could arise much more generically, from a scalar field with a simple potential, an energy landscape where the field starts at a high value, rolls slowly downhill toward its minimum, and drives exponential expansion during the slow roll. Chaotic inflation is robust and flexible, and it connects naturally to ideas about what might have preceded or surrounded our inflationary event, as we will explore later. Inflation ends when the inflaton field reaches the bottom of its potential energy. Well, the true vacuum and its energy is deposited into the particles of the standard model. This process is called reheating, and it is the moment that marks the beginning of the hot Big Bang as most people picture it. The fireball of matter and radiation that then evolved into galaxies, stars, and planets was not the beginning. It was what came after inflation ended. The Big Bang, in this picture, is not the creation of the universe. It is the thermalization of inflation's energy into ordinary matter. The universe existed, in some sense, before the Big Bang during the inflationary epoch as a nearly featureless, rapidly expanding expanse of vacuum energy. Reheating has observable consequences. The energy of inflation did not flow uniformly into matter and radiation. Quantum mechanics, which operates everywhere and always, introduced tiny fluctuations into the inflaton field during its slow roll. These are not engineering imperfections. They are fundamental. The uncertainty principle guarantees that no quantum field can be perfectly uniform. The fluctuations in the inflaton field were, during inflation, stretched from subatomic scales to cosmic scales by the expansion. After reheating, they became fluctuations in the density of matter regions, slightly denser and slightly less dense than average, spread across the universe at scales set by the rate and duration of inflation. These density fluctuations are what eventually grew, under gravity, into the large-scale structure of the universe, the filaments, sheets, and clusters of galaxies we see today, and their statistical properties, specifically their amplitude and how that amplitude varies with scale, are directly measurable in the CMB. The Planck satellite measured what is called the primordial power spectrum, characterized by a spectral index designated n sub s. Inflation predicts a nearly scale-invariant spectrum, one where fluctuations have roughly the same amplitude at all scales, with a slight tilt toward less power at smaller scales. Planck measured the spectral index as 0.9649 plus or minus 0.0042. The prediction of simple inflationary models is a spectral index slightly less than 1. The measurement is 0.9649. The agreement is extraordinary. Inflation also predicts primordial gravitational waves, ripples in the fabric of spacetime, generated by the same quantum process that produced density fluctuations, but manifesting as tensor perturbations rather than scalar ones. These gravitational waves would leave a specific imprint on the polarization pattern of the CMB, called B-mode polarization. This has not been definitively detected as of the date of this script, though the search is ongoing with instruments like BICEP and the Simons Observatory. Detecting it would measure the energy scale of inflation directly, a Nobel Prize-worthy result, and almost certainly within reach of the next generation of CMB experiments. But here is the line that ties all of this to our central story. Every fluctuation that inflation stretched to cosmic scales, every perturbation that became a galaxy or a cluster of galaxies or a cosmic void, each of these was once a quantum fluctuation smaller than an atom. Inflation is the mechanism by which the quantum becomes cosmic, and while it was doing that for the region that became our observable universe, it was doing the same thing for the vastly larger regions that inflation stretched beyond our horizon. Those regions contain their own quantum fluctuations, their own density perturbations, their own structures that formed from the same physics as ours, that evolved under the same laws, but that we will never see. Inflation created both the universe we can see and the boundary we cannot cross. Part 7. The minimum size of reality. In 2011, 3 cosmologists, Mihran Vardanyan, Roberto Trotta, and Joseph Silk, published a paper that attempted to answer a deceptively simple question. Given everything we know, given the measurements from Planck and WMAP and the whole suite of cosmological observations, what is the minimum size the actual universe could be? They used a statistical framework called Bayesian model comparison, which is a rigorous way of asking which hypothesis is best supported by the data, while penalizing hypotheses that require many adjustable parameters. They considered a range of models for the global geometry and topology of the universe, and they asked what minimum size was required for each model to be consistent with the observational data, specifically with the constraint that the universe appears flat to within the measured precision. The number they arrived at is the one we introduced at the outset. The universe must have a radius at least 251 times the radius of the observable universe. 251 times 46.5 billion light-years. That gives a minimum radius of approximately 11.7 trillion light-years. And the volume scales as the cube of the radius, so the minimum volume is 251 cubed, roughly 15.8 million times the volume of our observable sphere. 15.8 million observable universes, minimum, packed into the actual universe. Let's think about that for a moment. 2 trillion galaxies in the observable universe, multiplied by 15.8 million. The minimum total number of galaxies in the actual universe, under this conservative estimate, is around 32 sextillion, that is 32 followed by 21 zeros. Every single one of them invisible to us, not because our telescopes are too small, but because inflation pushed them beyond the boundary of causal contact. And these are not exotic, unusual galaxies. They formed from the same physics, the same initial conditions, the same quantum fluctuations stretched to cosmic scales by the same inflationary epoch. They are, statistically speaking, much like the galaxies we do see, ordinary, invisible, forever inaccessible. And 251 times the observable radius is, to be clear, the lower bound, the number you get from the simplest inflationary models, assuming the curvature is at the edge of the observationally allowed range. Most inflationary models, especially those where inflation lasted longer or began from initial conditions further from flatness, predict vastly larger extensions. There is a class of predictions under infinite flat universe models where the actual universe is genuinely infinite. Not very large in the way we might informally use that word, but infinite in the strict mathematical sense, extending without limit in every direction, with no boundary, no edge, no furthest galaxy. An infinite universe has a consequence that takes a moment to absorb. In an infinite universe filled with matter distributed roughly uniformly on large scales, every possible configuration of matter and energy will repeat not just once, but infinitely many times, including exact copies, including a Milky Way galaxy with a solar system and a planet, and a species that built telescopes and is watching a video about the size of the universe. The distance to the nearest exact copy of our observable universe, in an infinite flat universe, has been estimated at roughly 10 to the power of 10 to the power of 118 meters, a number so large that it cannot be visualized and barely can be written. Yet in an infinite universe, it is just a finite distance, not infinite, just very, very, very large. This is not mysticism. This is the direct, logical implication of combining an infinite universe with the observed uniformity of the CMB and the known laws of quantum mechanics, which limit the number of possible quantum states in a finite volume. If the universe is infinite, Repetition is not a philosophical concept. It is an inevitable mathematical consequence. We do not know if the universe is infinite. What we know is that it is at least vastly larger than anything we can see. The inflationary solution to the flatness problem that makes our existence possible is the same mechanism that guarantees most of the universe's content, most of its galaxies, most of its stars, most of whatever structures and histories and possible forms of complexity it contains are permanently beyond our reach. The map, to repeat what we established early on, is radically incomplete. And what is off the map is not featureless. It is more of the same. More galaxies, more complexity, more history, more of everything just permanently invisible from here. Part 8. Folded Space, the Universe that Loops. So far, we have been assuming that space, beyond our observable horizon, simply continues the way it does inside it, an ever-extending expanse, either infinite or at least vastly larger than anything we can see. Just more of the same, stretching outward in every direction without end. And that assumption is not unreasonable. It is, in fact, the default, the path of least resistance. The thing you get if you take the flatness measurement from Planck and just let it run. But there is another possibility, one that does not require the universe to be infinite and does not require it to have an edge. What if the universe is finite, genuinely, countably finite in volume but has no boundary? What if space folds back on itself, so that if you travelled far enough in a straight line, you would eventually arrive back where you started? I know that sounds like science fiction. It is not. It is a mathematically rigorous possibility that has been taken seriously by cosmologists for decades, and it connects to a distinction in mathematics that is worth understanding properly, because once you see it, it changes how you think about the shape of everything. The distinction is between geometry and topology. These two words are often treated as synonyms in casual conversation, but in mathematics they refer to genuinely different things, and conflating them is the source of most of the confusion around this topic. Geometry describes the local curvature of space. It tells you whether parallel lines will converge, diverge, or stay parallel. It tells you whether the angles of a triangle add up to 180 degrees or something different. It is about the rules of measurement that apply in the small, in the neighborhood around any given point. Topology describes the global shape, how the space is connected at the largest scales. It is not about what happens between two nearby points. It is about what happens if you keep going in one direction for a very, very long time. And here is the key insight that makes this interesting. The same local geometry can correspond to many completely different global topologies. Local flatness does not determine global shape. Those are separate questions, answered by separate mathematics. Let me give you a concrete example that makes this intuitive. Take a flat, two-dimensional surface. The simplest topology for a flat surface is an infinite plane. It extends forever in every direction, flat as far as you can go. If you lived on it and drew triangles, every triangle would have angles summing to 180 degrees, totally flat, totally Euclidean. But there is another topology for a flat surface. Take a square piece of paper. Connect the left edge to the right edge. You get a cylinder. Now take that cylinder and connect the top circle to the bottom circle, bending it around until they meet. What you get is a torus, the surface of a donut. And here is the remarkable thing. That surface is still locally flat. If you lived on it and drew a small triangle small enough that it did not wrap around the shape, its angles would still sum to 180 degrees. You could not tell, from local measurements alone, that you were living on a torus rather than a plane. But if you started walking in one direction and kept going, eventually you would arrive back where you started. The surface is finite. It has no edge, no boundary, no point where space simply stops. But it wraps around on itself in a way that makes it finite in area. Now extend that idea to 3 dimensions. This is harder to visualize because we do not have a convenient fourth spatial dimension to fold through, but the mathematics is perfectly well defined. A 3-torus, sometimes called a hypertorus, is the three-dimensional analog of the same construction. Imagine a cube. Identify the left face with the right face, the top face with the bottom face, and the front face with the back face. If you walk through the right wall, you reappear through the left. If you float up through the ceiling, you drop back in through the floor. The space is locally flat. Every local measurement satisfies Euclidean geometry, consistent with what Planck measured, but globally connected in this looping, wraparound way. The universe would be finite in volume. It would have no center and no edge. And it would be, if you have ever played the original Pac-Man, exactly like that video game screen where walking off one edge brings you back on the opposite side, except in all three spatial dimensions simultaneously. This is not a fringe idea. The possibility of a toroidal universe was explored seriously by two of the most respected Soviet cosmologists of the 20th century, Yakov Zeldovich and Alexei Starobinsky, in the 1970s and 80s. Starobinsky, incidentally, is the same physicist who developed one of the most successful models of cosmic inflation. These were not people working at the margins of the field. They were central figures, and they found the idea of a topologically non-trivial universe worth taking seriously on mathematical and physical grounds. The reason it matters observationally is that a toroidal universe would leave a specific fingerprint in the cosmic microwave background. If space loops back on itself at a scale comparable to or smaller than our observable sphere, then when we look out in certain directions, we would be looking at the same region of space approached from two different paths, one going the short way around the loop, one going the long way. The CMB temperature pattern in those directions would be identical because it is the same physical region. What you would see, if you knew how to look for it, is pairs of circles on opposite parts of the sky where the temperature pattern matches exactly like finding the same fingerprint in two places. Cosmologists call these matched circles, and they are the definitive observational signature of a finite, topologically non-trivial universe. The Planck satellite looked for them. Its topology analysis, published in 2015, searched the CMB sky systematically for these matched circle pairs across a wide range of angular scales. It did not find them, and this is where the result gets interesting in a subtle way, because the non-detection is not a refutation, it is a constraint. What Planck's non-detection tells us is that any topological identification scale the distance at which space loops back on itself must be larger than about 1.2 times the diameter of our observable sphere. In other words, if the universe is a 3-torus, the loops are too big to show up within the region we can see. The matched circles, if they exist, are sitting just beyond our horizon. We cannot rule out a toroidal universe. We can only rule out a small one. And given what inflation almost certainly did to the universe's size, a toroidal universe with loops that exceed our observational reach is entirely consistent with everything we know. Inflation would have stretched the topological scale along with everything else, pushing any loop structure well beyond the causal boundary. The two ideas, inflation and finite topology, are not in tension. They can coexist comfortably. There are even more exotic topological possibilities that have been explored. The Picard horn is one of them, a three-dimensional mathematical space that has the shape, roughly speaking, of an infinitely long trumpet. It has finite volume, but an infinite funnel stretching in one direction. Researchers have investigated whether its specific mathematical properties might match some of the anomalies seen in the CMB at the largest angular scales. Specifically, the fact that the biggest fluctuation modes in the CMB have slightly less power than simpler models predict. These large angle anomalies have occasionally been interpreted as hints of finite topology. The Picard horn models have not found compelling observational confirmation, but they have not been definitively ruled out either. They remain what you might call technically alive. The large-angle CMB anomalies deserve a moment's attention on their own because they sit in the data persistently across multiple independent analyses. The quadrupole and octopole, the largest scale temperature variations in the CMB sky, have less power than a purely random, infinite universe would statistically produce. Whether this is a hint of finite topology, a statistical fluke, a foreground contamination artifact, or something else entirely, is genuinely unresolved. It is the kind of small, stubborn anomaly that cosmologists keep returning to, not because it demands a radical explanation, but because it does not go away with better data. And here is what ties all of this back to the central thread of the story. Even if the universe is finite and topologically connected, even if space genuinely does loop back on itself at some vast scale, inflation still determines what portion of that structure we can observe. Topology and inflation are answering different questions. Topology describes the global architecture of space. Inflation describes the causal horizon, the boundary within which any signal can have reached us since the universe began. Those two things are logically independent of each other. A toroidal universe could be finite, with a perfectly well-defined total volume, and yet inflation could have pushed our observational horizon well inside a single topological cell. In that case, everything observable to us would look exactly the same as it would in a genuinely infinite flat universe. The wraparound structure would exist. It would be a real feature of the universe's global geometry, and we would have no way of detecting it from here. Not because our instruments are insufficient, because the causal boundary built by inflation sits closer to us than the scale at which the topology becomes apparent. The hidden majority of reality is hidden not by its topology, it is hidden by the causal boundary that inflation built into the structure of space-time. Whether the universe beyond that boundary is infinite, or finite and looping back on itself, or something more exotic still, the boundary itself is the thing. Inflation drew the line, and everything we are exploring, every model and measurement and anomaly and geometric possibility, is our attempt to reason about what is on the other side of a wall we built ourselves, without meaning to, in the first fraction of a second of existence. Part 9. Eternal Inflation and the Multiverse Layer. There is a further consequence of inflation that takes us to the edge of what can currently be tested and possibly past it. But before you tune out at the word multiverse, I want to be clear about something. What we are about to discuss does not begin with speculation. It begins with the same mathematics that makes inflation compelling in the first place. It follows, step by step, from the same quantum physics that produced the density fluctuations we measure in the CMB. The multiverse is not something cosmologists invented because it sounded exciting. It is something the equations keep insisting on, whether they are invited to or not. It is called eternal inflation, and it is, in some ways, the most radical implication of everything we have covered so far. To understand it, you need to go back to the mechanics of how inflation works in the models that best fit the data. The leading class of inflationary models, the ones whose predictions align most closely with what Planck measured in the CMB, are called slow-roll inflation models. The name describes the behavior of the inflaton field, the quantum field whose energy is responsible for driving the exponential expansion of space in the early universe. In these models, the inflaton field starts at a high value on its potential energy landscape. Think of it as a ball sitting high on a very gently sloping hill, and it rolls slowly downward toward the minimum. While it is rolling slowly, its energy is high and relatively constant, and that high, constant energy is what drives the exponential expansion of space. Inflation lasts as long as the field is slowly rolling. When the field reaches the bottom of the hill, inflation ends, the field's energy is transferred into matter and radiation, and the hot Big Bang begins. That is the classical picture. But quantum mechanics does not care about the classical picture. Quantum mechanics imposes something on top of the smooth classical rolling. It imposes fluctuations. The inflaton field, like every quantum field, cannot be perfectly uniform and perfectly smooth. The uncertainty principle forbids it. So as the field rolls classically downhill, quantum fluctuations ripple through it constantly, randomly nudging the field value up or down around its classical trajectory. In most places and at most times, the classical rolling wins, the field moves downward, and inflation ends on schedule. Those fluctuations are small perturbations on top of a dominant classical trend, and they are exactly the fluctuations that, when stretched to cosmic scales by inflation, become the density variations that eventually grow into galaxies. We have measured them. We know they are there. But here is what André Linde realized in the mid-1980s, and it is one of those moments in theoretical physics where a fairly simple observation has consequences so enormous they take years to fully absorb. In some regions of inflating space, the quantum fluctuations will not be small. They will, by random chance, be large enough to push the inflaton field back up the potential hill against the direction of classical rolling. Not most of the time, not even often. But quantum mechanics is probabilistic, and in a universe undergoing exponential expansion, rare events happen constantly, because there is always more space being created in which rare events can occur. Here is why that matters. Inflation is exponential. Space is doubling and doubling and doubling again, on timescales so short that the numbers barely translate into human concepts of time. In any given region, the chance that a quantum fluctuation kicks the inflaton field back up the hill, delaying the end of inflation in that region, might be very small. But the total volume of inflating space is growing exponentially. New inflating regions are being created faster than old ones are terminating. And in the regions where quantum kicks delay inflation's end, the same process applies again. Those regions keep expanding, keep producing new volume, and keep generating new quantum kicks, some of which will again delay the end of inflation locally. The consequence, which Linde worked out carefully and which has been elaborated on by many physicists since, is that inflation, once it starts, does not fully stop. It ends locally, in pockets regions where the classical rolling won, the field reached the bottom of its potential, and reheating occurred. Our observable universe is one of those pockets. The hot Big Bang we think of as the beginning of everything is, in this picture, not a beginning at all. It is a local ending of inflation, the moment when our particular region of inflating space transitioned into a hot, matter-filled cosmos. But surrounding that pocket, and surrounding every other pocket, inflation continues. It is always ending somewhere, and always beginning somewhere else. The process is self-reproducing, self-sustaining, and by the mathematics, eternal into the future. Cosmologists call it eternal inflation, and the structure it produces is sometimes called the inflationary multiverse, or the multiverse of pocket universes. Each pocket universe begins with its own version of reheating its own local Big Bang, its own initial conditions set by the specific state of the inflaton field in that region at the moment inflation ended. And this is where the picture becomes genuinely startling, because those initial conditions are not necessarily the same in every pocket. String theory, the leading candidate for a theory of quantum gravity, though still unconfirmed, predicts an enormous landscape of possible vacuum states. A vacuum state, in this context, is not empty space in the everyday sense. It is the lowest energy state of a particular configuration of the fundamental fields of physics. Different vacuum states correspond to different values of the physical constants, different strengths of the electromagnetic force, different masses for elementary particles, different values of the cosmological constant. The number of possible vacuum states that string theory's landscape contains is estimated at around 10 to the power of 500. That number is so large that writing it out in standard notation is essentially meaningless. For comparison, The total number of atoms in the observable universe is around 10 to the power of 80. The landscape of string theory dwarfs that by an incomprehensible margin. In the eternal inflation picture, when a pocket universe forms and reheating occurs, the inflaton field's energy is deposited into whichever vacuum state that region of space settles into. Different pockets, forming at different times and places in the eternally inflating background, may settle into different vacua, which means they would have different physics, different values of the fine structure constant, which governs the strength of electromagnetism, different electron masses, different strengths of the strong nuclear force, potentially different numbers of large spatial dimensions, different cosmological constants, different amounts of dark energy built into the fabric of space itself. They would be universes in the fullest sense, governed by their own physical laws, evolving according to their own constants, producing their own structures or failing to produce any, if their constants landed in regions of the landscape incompatible with complexity. This is what physicists mean when they talk about the string theory landscape in a cosmological context. It is not just a catalogue of mathematical possibilities. In the eternal inflation framework, it is a catalogue of actual places pocket universes, each one a cosmos unto itself, each one permanently inaccessible from every other one, separated not by distance, but by the inflating background that will always lie between them. Whether any of this is testable is the sharpest question in the field, and the honest answer is that direct confirmation is probably beyond any experiment we can conceive of. But indirect evidence is not impossible, and one candidate deserves attention. In eternal inflation, bubble universes, the pocket universes forming within the inflating background, are predicted to occasionally collide. As each bubble nucleates and expands, it can, in certain configurations, intersect with adjacent bubbles. A collision between two bubble universes would deposit energy asymmetrically into the CMB of each, leaving a specific circular imprint on the temperature or polarization pattern of the sky. A disk of slightly anomalous temperature, with a distinctive profile at its edge, in a region that would otherwise be statistically uniform. The CMB cold spot has been raised as a candidate. It is a region roughly 5 degrees across in the southern sky that is anomalously cold, colder than virtually any standard inflationary model predicts for a region of that size. It was identified by Vielver and colleagues in 2004 and confirmed by subsequent analyses. Current scientific consensus leans toward a large supervoid at a redshift of around 0.2 as the more likely culprit, a region of space with below average matter density, through which CMB photons lost energy via a mechanism called the integrated Sachs-Wolf effect. That explanation is well supported by galaxy surveys that have found underdense structure in that direction, but it does not fully account for the temperature deficit. The cold spot remains slightly colder than the supervoid alone explains, and the bubble collision hypothesis, while disfavored, has not been definitively ruled out. That is where we are. The multiverse is a prediction, not a confirmed reality, but a genuine prediction, one that follows from eternal inflation, and eternal inflation follows from the quantum physics that inflation requires to generate the fluctuations we actually observe. It is not arbitrary speculation dressed up in mathematical clothing. It is the logical end of a chain of reasoning that begins with the Planck satellite's measurement of the CMB spectral index and ends somewhere cosmologists are still working out how to think about. Some physicists remain deeply skeptical, not because the mathematics is wrong, but because a prediction that cannot be tested raises uncomfortable questions about what physics is supposed to do. If we can never design an experiment that distinguishes one of many bubble universes from the only universe in which inflation happened once, then what kind of claim is it? That debate is real, unresolved, and worth taking seriously rather than hand-waving away. What it represents, whatever its ultimate status, is the outermost layer of the consequence of inflation. Not just more space beyond our horizon, not just more galaxies cut off by the causal boundary, but the possibility that the hiddenness of reality extends past the merely spatial, past the merely large, into something categorically different, other spacetimes, other physics, other versions of the constants that make atoms stable, stars luminous, and chemistry possible. The boundary inflation built inside our universe may be the smallest of the walls. Beyond it, if eternal inflation is correct, lies a structure so large and so varied that our entire observable universe, 2 trillion galaxies, 46 billion light-years of depth, 13.8 billion years of history, is not even a rounding error in its total account. And we are sitting here, inside our bubble, reading its walls for clues. Part 10. The Anomalies at the Edge. The cosmic microwave background is the most studied object in all of cosmology, not the most studied object in our solar system, not the most studied object in the Milky Way, the most studied object full stop in the entire history of human scientific inquiry. It has been mapped by 3 generations of dedicated experiments, each one more sensitive than the last. It has been analyzed by hundreds of independent research groups across dozens of countries, using every statistical tool that modern cosmology has been able to devise. Papers about the CMB are published every week. Careers are built on its subtler features. There are physicists who have spent their entire professional lives studying temperature variations smaller than 1 part in 100,000, arguing about the significance of structures that span less than a degree on the sky. And mostly, remarkably, almost breathtakingly mostly, it agrees. The standard cosmological model, with its flat geometry, its inflation-generated perturbations, its cold dark matter, and its cosmological constant, produces predictions for the CMB that match observation with a precision that should honestly make you stop and marvel at what physics has accomplished. The acoustic peaks in the power spectrum sit exactly where they should. The spectral index of the primordial fluctuations matches the slow roll inflation prediction to within a fraction of a percent. The polarization pattern agrees with the temperature pattern in the way that the physics demands. For a model built on events that happened 13.8 billion years ago, in conditions we cannot replicate in any laboratory, the agreement is extraordinary. But not entirely. There are anomalies. They are small enough that no single one of them, standing alone, would compel you to abandon the standard model. But they are persistent, showing up independently in WMAP data, and then again in Planck data, appearing in one analysis method, and then again in a completely different one, sitting stubbornly in the numbers after every known source of contamination has been carefully removed. They are the kind of anomalies that serious scientists do not dismiss, because the history of physics is full of cases where a small, persistent discrepancy in clean data turned out to be the first whisper of something genuinely new. And in this case, the genuinely new thing that some of them might be whispering about is the most interesting possible thing: structure, or physics, or events beyond the boundary of what we can ever directly observe, leaving fingerprints inside the bubble we are trapped in. Let's go through them properly, because they each have their own character and their own story. The CMB cold spot is the most discussed and probably the most visually striking. It was identified in 2004 by Patricio Vielva and colleagues, working with data from the WMAP satellite. Using a mathematical tool called a spherical Mexican hat wavelet, a filter designed to highlight features at specific angular scales, they found a region in the southern CMB sky, roughly centered on the constellation Eridanus, that was anomalously cold. The region spans approximately 5 degrees across, which sounds small, but in CMB terms is enormous. 5 degrees is 10 times the width of the full moon, and it is cold in a way that goes beyond ordinary CMB variation. The temperature deficit there is larger than statistical models of the CMB, based on the standard inflationary model predict for a region of that size. The probability of such a feature occurring by chance, just bad luck in the random distribution of primordial fluctuations, has been estimated at somewhere between 1 and 2%. 1 to 2% is not impossible. It happens. If you flip a coin 50 times and get 40 heads, that's unlikely, but it can occur. The cold spot alone is not proof of anything, but it has attracted sustained attention because the mundane explanations for it do not quite close the case. The leading candidate explanation is a supervoid, a large region of space at a redshift of around 0.2, containing significantly below average matter density. When CMB photons travel through a void, they lose energy. They have to climb out of a shallow gravitational well as the universe expands and the well flattens, and they come out the other side slightly colder. This mechanism is called the integrated Sachs-Wolf effect, and it is well-established physics. Galaxy surveys have found evidence for an underdense region in the direction of the cold spot, and that has shifted the consensus toward the supervoid as the primary explanation. But the supervoid does not fully account for the temperature deficit. The cold spot is still slightly colder than the supervoid alone predicts. The gap is not huge. It is not screaming at us, but it has not gone away with more data, and it has kept a small but rigorous community of physicists asking whether something else is contributing. The bubble collision hypothesis, a collision between our pocket universe and an adjacent one in the eternal inflation framework, predicts exactly this kind of feature. A circular region of anomalous temperature with a specific profile. It has not been confirmed. It has not been ruled out. The axis of evil is a different kind of anomaly, and in some ways a more unsettling one, because it is not about a single cold patch in one corner of the sky. It is about the largest scale structure of the entire CMB map. When you decompose the CMB temperature pattern, mathematically breaking it down into components at different angular scales, the way you might decompose a musical chord into its individual notes, you get a hierarchy of structures. The largest scale components are called the quadrupole and the octupole. The quadrupole represents the broadest temperature variation across the sky, the gentlest wave. The octupole is the next scale down, slightly finer. In a universe whose initial conditions were generated by inflation, a process that is, by its nature, completely isotropic, with no preferred direction in space, these components should point in random directions. The quadrupole's axis and the octupole's axis should be statistically independent of each other, and both should be statistically independent of anything in our local cosmic neighborhood. They are not. When the WMAP data first revealed this, and Planck later confirmed it, the quadrupole and octupole were found to be aligned with each other to a degree that is statistically improbable in a purely random field. More striking still, both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sunday. The probability of this occurring by chance, in a genuinely isotropic universe, is less than 1%. The anomaly was dubbed the axis of evil, a name that has stuck partly because of its drama and partly because of its implication that the largest scale structure of the universe appears to know which direction our solar system is pointing. The obvious first response is foreground contamination. If emission from within our own solar system or from the plane of the Milky Way is leaking into the CMB maps, it would naturally correlate with the ecliptic and the galactic plane. Cosmologists have worked extremely hard to remove these foregrounds, using multiple independent methods, and the anomaly persists. It is reduced foreground removal does chip away at it, but it does not disappear. It remains, residually, in the cleaned maps across multiple independent analyses. Whether the residual is a systematic artifact that no one has quite managed to model correctly, or a genuine feature of the primordial CMB, is a question that does not yet have a settled answer. The third anomaly is more recent, and it arrived not from the CMB itself, but from a completely independent dataset, the large-scale distribution of distant quasars. Quasars are among the most luminous objects in the universe, the intensely bright cores of galaxies powered by actively accreting supermassive black holes. They can be seen at enormous distances, making them ideal tracers of the large-scale structure of the universe. A study using the CatWise catalog, a catalog of infrared sources built from data taken by NASA's Wide Field Infrared Survey Explorer, looked at the distribution of quasars across the sky and measured their dipole, the asymmetry between the number of quasars in one direction versus the opposite direction. Our motion through the universe produces a known dipole signal in the CMB, and it should produce a corresponding predictable dipole in the distribution of distant sources. The two should agree. They do not. The dipole measured in the quasar distribution is approximately 4 standard deviations larger than the CMB dipole predicts it should be, 4 sigma. That is not a rounding error. That is not a small discrepancy that gets absorbed into error bars. It is a significant mismatch between what our motion through the universe should produce and what the distribution of matter at the largest observable scales actually shows. The two main interpretations are either a systematic effect in the data, some instrumental or calibration artifact that is mimicking a physical dipole, or a genuine large-scale anisotropy in the distribution of matter, an asymmetry that extends to the furthest distances we can map. If the latter, it would suggest that the universe is not perfectly homogeneous and isotropic at the largest scales, which is one of the foundational assumptions of the standard cosmological model. None of these anomalies have crossed the 5 sigma threshold that physicists require before claiming a discovery. That threshold exists for good reason. With enough data and enough tests, flukes happen, and the history of physics is also full of 3 sigma anomalies that quietly disappeared with more data. It is entirely possible that all 3 of these features have mundane explanations that will become clear as surveys improve and analysis methods sharpen. But it is also possible that they are not flukes. It is possible that they are, in some sense, signals, not random noise, not uncorrected foregrounds, but genuine imprints of something at or beyond the boundary of our observable universe. A topology that makes the largest scales of our observable sphere feel the influence of what lies just outside, an inflationary geometry that was not perfectly symmetric on scales slightly larger than our horizon, a bubble collision that left its mark and is waiting to be confirmed. The possibility that some of these anomalies represent the faint, distorted fingerprints of physics beyond the causal boundary is one that a small but serious group of cosmologists continues to investigate with real mathematical rigor, not as fringe speculation, but as a legitimate open question in the data. The universe has left its fingerprints inside our bubble. Most of them spell out the standard model, precisely and clearly, but a few of them are slightly smudged, in ways that the standard model alone does not quite explain. And in science, it is almost always the smudges that lead somewhere interesting. Part 11. The universe is still expanding away from itself. Everything we have discussed so far has treated the size of the observable universe as a fixed fact, a number determined once and for all by the age of the universe and the history of inflation, stamped into the structure of space-time and left there permanently. 46.5 billion light-years, 2 trillion galaxies, a sphere whose boundary was drawn in the first fraction of a second of existence and has not changed since. That is not quite right. The observable universe is not static, it is changing, and it is changing in a direction that makes everything we have been talking about, the hiddenness of reality, the progressive inaccessibility of most of what exists, progressively worse with every passing year. Not dramatically worse, not in any way you would notice on a human timescale, or even on the timescale of recorded history, or even on the timescale of our species' existence. But cosmologically, inexorably, the window is closing, and the mechanism responsible is one of the strangest and most consequential discoveries in the history of physics. It is called dark energy, and before we get into what it does to the future of the observable universe, we need to sit with what it actually is, or rather, with the deeply uncomfortable fact that we do not really know. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. That sentence contains a word that should stop you. Accelerate. Not just expand, accelerate. The universe is not only getting bigger, it is getting bigger, faster, and has been for roughly the last 5 billion years. We know this because of supernovae, a specific type called Type Ia supernovae, produced when a white dwarf star in a binary system accretes enough mass from its companion to exceed a critical threshold and explode. These explosions are remarkably consistent in their intrinsic brightness, consistent enough that by measuring how bright they appear from Earth, we can calculate how far away they are with considerable precision. They are, in the language of cosmology, standard candles, reliable distance markers scattered across the universe. In 1998, 2 independent teams were using Type Ia supernovae to map the expansion history of the universe. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z supernova team, led by Brian Schmidt and Adam Rees, were both trying to measure how fast the expansion of the universe was slowing down. This was a reasonable thing to try to measure, because gravity should be slowing it down. Everything in the universe is pulling on everything else. You would expect that mutual attraction to gradually put the brakes on the Big Bang's initial expansion, like a ball thrown upward that slows as gravity pulls it back. Both teams expected to measure a deceleration. They expected to find that distant supernovae were slightly brighter than a non-decelerating universe would predict, because a slowing expansion means they are slightly closer than you would naively estimate. Instead, both teams independently found the opposite. The distant supernovae were fainter than expected. Fainter means farther. Farther, at those distances, means the universe was expanding more slowly in the past than it is today, not decelerating. Accelerating. Something was pressing the accelerator rather than the brakes, and had been doing so for billions of years. Both teams were sufficiently alarmed by their own result that they spent considerable time looking for errors before accepting it. They found none. The discovery won the Nobel Prize in Physics in 2011, awarded jointly to Perlmutter, Schmidt, and Rees, and it remains one of the most genuinely shocking results in the history of modern science. Whatever is causing the acceleration has been named dark energy, a label that is honest about how little it tells us. Dark energy is not dark matter. Dark matter is a form of matter that does not interact with light, but does interact gravitationally, clustering around galaxies and influencing their rotation. Dark energy is something different and stranger, a form of energy that permeates all of space uniformly, does not dilute as space expands, and exerts a kind of negative pressure, a repulsive effect on the geometry of space-time that drives acceleration rather than deceleration. It currently accounts for approximately 68% of the total energy content of the universe. Most of what the universe is made of is something we have no confirmed physical explanation for. The simplest model for dark energy is Einstein's cosmological constant, which Einstein himself introduced into his equations of general relativity in 1917, originally as a fudge factor to produce a static universe, then famously abandoned when Hubble's observations revealed that the universe was expanding, then resurrected by the supernova results. In the cosmological constant model, dark energy is the energy of empty space itself, the vacuum energy of quantum fields, a baseline hum of energy that exists even when all matter and radiation have been removed from a region. It is characterized by an equation of state parameter, designated W, equal to -1, meaning its pressure is exactly equal and opposite to its energy density in a way that produces the observed acceleration. The cosmological constant model fits the data reasonably well, but it comes with a problem so severe that physicists call it, without much exaggeration, the worst prediction in the history of science. Quantum field theory, the framework that describes all known particles and forces with extraordinary precision, predicts a vacuum energy density that is approximately 120 orders of magnitude larger than the value we observe for dark energy. 120 orders of magnitude. That is not a small discrepancy. That is the kind of discrepancy that suggests something is fundamentally missing from our understanding. Either quantum field theory is wrong about vacuum energy in some profound way we do not yet understand, or there is some mechanism that cancels the predicted vacuum energy almost, but not quite completely, leaving just the tiny residual we observe. No one knows what that mechanism is. This is the cosmological constant problem, and it sits at the center of theoretical physics as one of the deepest unsolved puzzles in the field. This is part of why the results coming from the dark energy spectroscopic instrument DESI have attracted so much attention. DESI is conducting the largest spectroscopic survey of the universe ever attempted, mapping the three-dimensional positions of tens of millions of galaxies across a huge volume of cosmic history, using the imprint of baryon acoustic oscillations, those frozen sound waves from the early universe, to trace how the expansion rate has changed over time. The survey is designed to measure dark energy's equation of state parameter W with unprecedented precision, and to detect whether W has been constant over cosmic history or whether it has evolved. The first year of DESI data, released in 2024, produced a result that stopped people in the field. The data showed a hint, not a confirmed detection, but a statistically interesting hint that W is not exactly -1, and that it may be evolving with time. A value of W that changes over cosmic history would rule out the simplest cosmological constant model, which by definition cannot evolve. It would imply that dark energy is not the energy of empty space, but something more dynamic, a field, perhaps, that changes its value as the universe ages. The significance of the DESI hint is not yet at the 5 sigma threshold required for a confirmed discovery, but it is consistent across multiple independent analysis approaches within the dataset, which makes it harder to dismiss as a statistical artifact. The cosmological community is watching the next releases of DESI data with considerable interest. The leading class of dynamical dark energy models goes by the name quintessence. In these models, dark energy is a scalar field, not unlike the inflaton field that drove inflation in the early universe, that is slowly rolling down its potential energy landscape, driving accelerated expansion as it does so. The structural parallel between inflation and quintessence is striking and has not gone unnoticed by theorists. Both invoke a slowly rolling scalar field. Both produce an epoch of accelerated expansion, one in the very early universe, one in the late universe. Both leave observable signatures in the large-scale structure of the cosmos. This similarity has motivated a class of unified models, sometimes called quintessential inflation, in which a single scalar field is responsible for both epochs, driving the exponential expansion of inflation at the beginning, then settling into a slowly rolling phase that produces the gentle, accelerated expansion we observe today. Whether such unified models are correct is unknown, but the fact that the same mathematical structure appears to be operating at both ends of cosmic history is the kind of pattern that theoretical physicists find hard to ignore. What all of this means for the observable universe and for the central story we have been building throughout this video is stark and in some ways melancholy. The cosmic event horizon, the boundary beyond which we can never again receive information, is currently shrinking in comoving terms. Galaxies that sit just inside that boundary today will, over the coming billions of years, drift across it and go dark, their light redshifted by the accelerating expansion until it stretches to wavelengths too long for any instrument to detect. The number of galaxies accessible to us in principle is decreasing with time, not increasing. We are not gaining observational reach as the universe ages, we are losing it. Project this forward far enough, and the picture becomes almost desolate. In roughly 100 billion years, about 7 times the current age of the universe, an almost incomprehensible span of future time, the only galaxies remaining visible in the sky will be those gravitationally bound to the Milky Way, the local group, a few dozen galaxies held together by their mutual gravity against the expansion of everything else. The Andromeda Galaxy, the Magellanic Clouds, a handful of smaller companions. Everything beyond that will have faded to invisibility, redshifted into silence by the relentless expansion of space. Future astronomers, if any exist, will look out at a sky containing far fewer galaxies than we see today, with no way of knowing, from their observations alone, that the universe ever contained the 2 trillion we can currently count. The evidence will be gone. The universe will have hidden its own history, and in the most extreme scenario, it does not stop there. If dark energy is not constant, but grows stronger over time, a model called phantom dark energy, characterized by W less than -1, then the acceleration does not merely continue, it intensifies. Eventually, it grows strong enough to overcome not just the gravitational binding between galaxies, but the binding between individual stars, between planets, between molecules, between atoms, and finally, between the quarks inside atomic nuclei. Everything tears apart, not through heat, not through collision, not through any conventional catastrophe, but through the literal expansion of the space between the components of matter. This is the Big Rip, the universe ending not in a bang, not in a cold fade, but in a dissolution so total that the last things to go are the fundamental particles themselves, shredded by the geometry of space-time. Whether dark energy is actually phantom in this way is unknown. Current data does not require it, but it does not rule it out. Even in the gentler scenarios, the trend is unambiguous and the direction is one way. The observable universe is becoming more isolated. The causal boundary that inflation built into the structure of space-time is being reinforced and tightened by dark energy. What inflation started the progressive hiddenness of reality, the structural concealment of most of what exists, dark energy, is continuing, faithfully and relentlessly, one accelerating megaparsec at a time. The universe is not just expanding away from itself. It is expanding in a way that guarantees the fraction of it any observer can access will only ever decrease. We happen to exist at a cosmologically fortunate moment early enough in the universe's history that the sky still contains 2 trillion galaxies, that the evidence of inflation is still legible in the CMB, that the large-scale structure of the cosmos is still visible in galaxy surveys. Later observers, if there are any, will inherit a smaller window, a quieter sky, and a universe that has done an even more thorough job of hiding itself. We are seeing more of it right now than anyone ever will again. Part 12. The final realization: the wall was built on purpose. Let's step back, not just from the last section, but from all of it, from the flatness problem and the knife-edge precision of 1 part in 10 to the 62, from inflation's exponential stretching and the factor of 10 to the 26th that it applied to space in less than a billionth of a second, from the CMB and its acoustic peaks, sitting exactly where flat geometry models predicted, from the 251 minimum radius and the 15 million observable universes worth of content that implies, from the topological possibilities, the hypertorus, the Picard horn, the Pac-Man universe wrapping back on itself at scales we cannot reach, from eternal inflation and the foam of pocket universes it produces, from the anomalies at the edge of the CMB map, the cold spot and the axis of evil and the quasar dipole, sitting in the data quietly and persistently, waiting for either a mundane explanation or a genuinely extraordinary one, from dark energy and its patient, relentless work of pushing galaxies beyond our causal reach, tightening the window with every passing eon. Step back from all of it and look at what it adds up to. Because taken together, these threads do not form a collection of separate puzzles. They form a single, coherent story. And it is a story about something more specific and more strange than the mere size of the universe. It is a story about why the universe we can observe is not an accident of technology, not a temporary limitation of our instruments, not a problem that the next generation of telescopes will solve. It is a structural feature of how space-time itself is organized. The hiddenness of most of reality is not incidental to this universe, it is constitutive of it. Let me say that again in plain terms, because it is the central thing, the same physical process that made this universe livable, that smoothed out its geometry, seeded its structure, created the conditions for stars and planets and carbon and us, is the same physical process that hid most of the universe from us permanently. Not temporarily, not until better instruments arrive. The boundary was built into the physics at the same moment the physics built us. Our existence and our ignorance are not separate facts. They are two consequences of one event, separated by nothing more than the direction you choose to look at the equations. The observable universe is a causal bubble. That is the most precise way to say what it is. It is the sphere defined by the maximum distance from which any signal, traveling at the speed of light through the expanding universe, could have reached us in the entire history of time since the universe became transparent. 46.5 billion light-years in radius. Everything inside that sphere has had, at some point, the possibility of causal contact with us. Some signal, some photon, some gravitational wave could, in principle, have travelled from there to here. Everything outside it has not. Not yet, and in most cases not ever, because inflation stretched those regions so far beyond our reach that the expansion of space will always outpace any signal they could send. The boundary is not a wall in the physical sense. There is no membrane, no barrier, no change in the texture of space at 46.5 billion light-years. If you could somehow travel outward fast enough and far enough, you would pass through regions that are currently beyond our horizon without noticing anything unusual about the space itself. Galaxies there, stars there, planets perhaps, physics operating exactly as it does here. The boundary is not a property of that space. It is a property of the relationship between that space and us specifically, of the fact that no information from there can reach here. The wall is made of causality, not matter. And causality, in a relativistic universe with a finite speed of information and a history of extreme spatial expansion, turns out to be one of the most absolute boundaries in nature. This is where the holographic principle enters the story, and it enters it in a way that elevates the horizon from a mere observational limitation to something with genuine physical reality. The holographic principle was first proposed by Gerard Hooft and Leonard Susskind in the 1990s, growing out of work on black hole thermodynamics and the question of what happens to information that falls into a black hole. The core idea is that all the information required to describe a volume of space is encoded on the two-dimensional surface that bounds it the way a hologram encodes a three-dimensional image on a flat surface. Volume and information do not scale together the way intuition suggests. The information content of a region scales with its surface area, not its volume. Juan Maldacina's work on what is called the AD-CFT correspondence in 1997 gave this idea its most mathematically rigorous formulation, showing that a theory of gravity in a certain type of curved space is exactly equivalent to a quantum field theory living on its boundary. The two descriptions, volume and surface, are not approximations of each other. They are exact duals, different mathematical languages describing the same physical reality. In the context of our universe specifically, in the context of de Sitter space, which is the mathematical description of a universe dominated by a positive cosmological constant, and which approximates what our universe is becoming. As dark energy increasingly dominates, there is a concept called de sitter, entropy. It assigns a specific, finite number to the total information content of everything within our cosmological horizon. And that number is proportional not to the volume of our observable sphere, but to its surface area, the area of the horizon itself. The boundary encodes the interior. The edge contains the information about everything inside it. What this means, if you take it seriously, is that the horizon is not just a limit on what we can see. It is a limit on what physically exists, in the information theoretic sense, from the perspective of any observer inside it. The boundary between the observable and the unobservable is not an arbitrary line drawn by the accident of our position in space and time. It is a surface with genuine thermodynamic significance, a surface that has a temperature, an entropy, and an information capacity. It is, in some deep sense, that physicists are still working out the full implications of physically real in a way that goes beyond the merely observational. So what lies beyond it? The honest, data-grounded answer has 4 layers, and they are worth laying out clearly and in order, from the most certain to the most speculative, because the difference in epistemic status between them matters. The first and most certain layer is simply more of the same, more space, structured by the same physics, seeded by the same inflationary perturbations, evolving under the same laws of gravity and electromagnetism and nuclear physics that operate inside our observable sphere. The Vardanyan, Trotter, and Silk analysis. The minimum radius constraint of 251 times our observable sphere implies at least 15 million observable universes worth of content sitting beyond our horizon, all subject to identical physical laws, all populated by galaxies and stars and whatever else those conditions produce, all permanently invisible to us. This is not speculation. This does not require any new physics. This is the minimum that follows from taking the Planck satellite's flatness measurement seriously and applying the mathematics of inflation to it. 2 trillion galaxies in our observable sphere multiply by 15 million. The number of galaxies in the actual universe, under the conservative estimate, is around 32 sextillion, 32, followed by 21 zeros. Every one of them governed by the same physics. Every one of them dark to us, not because our telescopes are too small, but because inflation put them there. The second layer is finite topology, the possibility that space, rather than extending infinitely, loops back on itself in a multiply-connected geometry. A hypertorus, a space where travelling far enough in any direction brings you back to where you started, like an enormous 3-dimensional version of the Pac-Man screen. This would make the universe finite in total volume, with no edge and no centre, locally flat in every neighbourhood, but globally wrapped in a way that our current observations cannot detect, because inflation has pushed any topological identification scale beyond our observational reach. In this scenario, what lies beyond our horizon is, eventually, us the same region of space approached from the other direction, after a cosmic journey around the loop. The universe as a hall of mirrors, except the mirrors are so far apart that the reflection has never had time to reach us. The third layer is the extended inflationary volume, the full scope of what the inflationary epoch created, which goes far beyond the 251 minimum. Inflation's duration and the energy scale at which it occurred are not precisely known. The minimum expansion factor of 10 to the 26th is a lower bound, not a best estimate. Many well-motivated inflationary models predict far larger expansion factors, thousands, millions, or billions of times the minimum. Regions that were causally connected to ours before inflation, that shared the same pre-inflationary patch, the same initial conditions, the same early equilibrium, were pushed beyond our horizon during inflation and have been receding ever since. They share our history up to the moment of inflation. After that, We cannot say. They evolved under the same laws, seeded by the same quantum fluctuations, but their subsequent 13.8 billion years of history are inaccessible to us. They are, in the most literal sense, parallel histories, not in the science fiction sense, but in the sense of histories running in parallel, separated by a boundary that physics will never let us cross. The fourth layer is the multiverse, the foam of pocket universes produced by eternal inflation, potentially each with different physical constants, different vacuum states, different versions of the fundamental forces. This is the most speculative layer and the one that sits most uncomfortably at the boundary between physics and philosophy. It follows logically from the same quantum mechanics that makes inflation produce density fluctuations. It is not arbitrary, but it may be permanently untestable in any direct sense, and that raises genuine questions, questions that serious philosophers of science take seriously about what kind of claim it is. Whether it is a scientific hypothesis or a mathematical extrapolation that happens to be consistent with observation is a debate that is ongoing and unresolved. Both things can be true simultaneously, and the discomfort of that is worth sitting with rather than resolving artificially in either direction. Here is what ties all four layers together into a single story. Every one of them is a consequence of the same physics. The flatness that required such extreme fine-tuning, the inflation that resolved the fine-tuning by exponentially stretching space, the causal boundary that the stretching built into space-time, the dark energy that is currently reinforcing that boundary and will continue to do so indefinitely. These are not four separate facts about the universe. They are four chapters of one story, told by one set of equations, applied consistently to one universe from its first moment to its last. And the story they tell, read all the way through, is that this universe is not hiding itself by accident. It is hiding itself by design, not in the theological sense, but in the physical sense. The concealment is structural. It is written into the equations of general relativity, quantum field theory, and the dynamics of inflation, as surely as the speed of light is written into Maxwell's equations. There is a question in the philosophy of science about what it would mean for something to be permanently unknowable. Not unknown because we lack technology, not unknown because we have not looked hard enough, but unknowable in principle because the answer is structurally beyond the reach of any possible observation. It is a question that used to feel academic, like a puzzle for philosophers who had run out of real problems. It no longer feels that way. The questions we have been circling in this video are in that category, not metaphorically, literally. We cannot build a telescope that sees beyond our causal horizon, because the light from beyond it has not reached us and never will. We cannot send a probe that returns data from beyond it, because no probe traveling at any achievable speed will ever cross the distance that inflation opened up. We cannot observe the total size of the universe, the topology of space beyond our observable sphere, the structure of other inflationary bubbles, the physical constants of other pocket universes. These are not questions waiting for better instruments. They are questions that the physics of our universe has placed, permanently and irrevocably, outside the boundaries of empirical access. And yet, and this is the thing that I find most remarkable about where physics has arrived, we are not without recourse, not completely, because the physics that governs what lies beyond our horizon also governs what happens inside it, and it leaves traces, fingerprints. The flatness we measure implies the extension we cannot see. The spectral index of the CMB perturbations confirms the inflationary origin of structure. The primordial gravitational wave background, if detected, would measure the energy scale of inflation directly and constrain the range of possible inflationary models, and with it, the probable size of the inflated volume. The matched circles in the CMB that would reveal topology, if they exist within our observable sphere. The bubble collision signatures that would hint at eternal inflation. The dynamics of dark energy, measured by dE psi and its successors, which constrain the nature of the field driving acceleration and its future behavior. The gravitational wave backgrounds, detectable by next-generation observatories, which may carry information from epochs earlier than the CMB, perhaps even from the inflationary epoch itself. We can infer what we cannot observe, and the inference, while incomplete, is not nothing. It is, in some ways, the most profound achievement of physics as a discipline that local equations, applied carefully to local observations, have consequences that extend far beyond what any experiment can directly confirm, and that those consequences can be tested through the imprints they leave in the local data. The universe is not cooperating with our desire to see beyond the horizon, but it has left its physics intact all the way to the edge, and those physics, read carefully, tell us more about what lies beyond than we have any right to know. The observable universe, 46.5 billion light-years in radius, 2 trillion galaxies, the surface of last scattering encoded in the CMB at a temperature of 2.7 Kelvin, 2 centuries of telescopic observation, 3 generations of CMB satellites, the most precise instruments any civilization we know of has ever constructed, is a window. It is a small window. It is a biased window because we are embedded inside it and cannot step outside to check the view. It is a bounded window because the physics that made it habitable also made it finite in causal reach. And it is, in all likelihood, a shrinking window, as dark energy continues its patient work of pushing more and more of the cosmos beyond the boundary that inflation established. But it is still a window, and what it looks out on what the equations say is on the other side of the glass is not emptiness, not silence, not a void. It is more universe, incomparably more. Universe that formed by the same physics, under the same laws, from the same initial conditions. Universe that has its own 13.8 billion years of history that we will never read. Universe that may, in the eternal inflation picture, vary in its physical constants and its fundamental character from pocket to pocket across a landscape of possibilities so vast that our observable cosmos is a single point within it. The wall is not the end of the story. It is the edge of the chapter we are in. The universe did not just grow too large to see. It grew in a way that guaranteed we never would. And perhaps the deepest thing to hold on to the thought worth carrying out of this video into whatever you do next is this. The fact that we know this is not a failure. It is not a limitation to be lamented. It is science doing exactly what science is supposed to do, following the mathematics wherever it leads, even when it leads past the edge of what any experiment will ever confirm, even when it leads to the uncomfortable conclusion that the most important questions about the structure of reality are permanently beyond our observational reach. The equations reveal their own limits. The data tells us not just what we see, but how much we are not seeing. Cosmology has reached the point where its greatest achievement, its most precise and confident result, is a measurement of its own boundary. The wall was not built to frustrate us. It was built by the same process that built us. The inflationary epoch that flattened our region of space, seeded the structure that became galaxies and stars and planets, and created the conditions for something like us to exist, that same epoch, in the same fraction of a second, drew the horizon that we will never see beyond. The observer and the boundary were created together. We are not separate from the thing that hides reality from us. We are a product of it. The observable universe is not a cage. It is a consequence. The question of what lies beyond it is not really a question about elsewhere. It is a question about why here exists at all. And the answer, as best the data and the mathematics can give it, is that here exists because the physics that made here possible also made everywhere else invisible. The universe has been explaining itself to itself through the only instruments it has ever produced that were capable of asking the question. We are those instruments. And if that is not enough, to fill a quiet night with something worth thinking about, then I am genuinely not sure what is.